welcome! On this channel I get quite often the request for a how-to about the first steps of a retro PC mainboard repair. Well, every case is of course different, and it's hard to make a how-to which would fit them all. I already made quite a lot of repair videos and hopefully every one of those was helpful in some ways, but in this video I would like to go through a typical order of steps which I usually take during such a repair. As an example for the repair today, I have this 386 mainboard. I took it from my to-do pile of hardware, and all I know about it currently that it is dead. However, it is a beautiful mainboard with its dark PCB and golden traces. A nice piece for a showcase, to be honest. This board seems to be in a mint condition. As you probably know, most of the mainboard repairs which I do starts with removing of a leaky battery, treating the board with white vinegar, washing it and restoring corroded traces. Luckily, this board has no battery at all, and so it never got a chance to be damaged by that. So this repair will not include those steps. However, if you're interested why I use white vinegar against leaky batteries, I made a video about this topic which you might find interesting. Sometimes a board is extremely dirty and needs to be washed first, but in this case it's not needed too. It is just a little bit dusty, so I skip a wash and go for the first step. Mainboard identification. As you can probably see by the CPU and FPU sockets, this is a 386DX mainboard. It is based on Intel chipset. Here we have a name 386L revision 1.1. This should already be very helpful. I use the Retro Web project for identification. This is the best resource where you can find thousands of mainboards with pictures, documentation, BIOS images and more. Many great people from the community have been working on this project since years and continue to contribute to it every day. A big thank you at this point to every one of them. So, what we have is a mainboard named 386L. Let's just search by name. And here it is, seems to be Elite Group Computer Systems, or short ECS 386L. Here we have documentation with jumper settings. BIOS image hasn't been yet uploaded. This is something what I could contribute after this repair. And here is the photo of the board, so I can look up something if I need to. For example, if some parts are missing and I need to find out what exactly. Nice, but what to do if you don't know the name of the mainboard? No problem, we just have to look up for some attributes. As I said, this is a 386DX board due to the sockets. Furthermore, we have 1, 2, 3, 4, 5, 6, 16-bit ISO slots, and furthermore another 2 8-bit ISO slots. This should be enough to set up some filters on the Retro Web search. So we go to the mainboard search. Type of processor family is 386DX. Add expansion slots 6 times 16-bit ISO. Add 2 times 8-bit ISO. And select show images. And search. I selected just a few attributes, and of course we see quite a lot of similar mainboards, but you can add more detailed information like chipset and other options to improve filtering. Anyway, thanks to the images you can visually go through the list very quickly. Yeah, and here is our board, so it is an ECS 386L. Interesting observation up front, the board in this entry has VLSI chipset, but the one I have has Intel chipset, though VLSI tag is also written on it. Most probably this is the same chipset made in cooperation and released under different names. Well, now where we identified the board, let's move on to the next step. Checking for shorts. One of the most common issues on the old mainboards are shorted tantalum capacitors, which can put power supply voltages to the ground. That's why it is important to check if there are any shorts between the power supply pins. For that matter, check out the pinout of the power connector. This is a standard AT power connector. In the middle you have 4 ground pins, and left and right from it there are ±5V, ±12V and power good pins. None of those should show you less than 10 ohm resistance to the ground. Usually it goes up to a kilo ohms, but I saw already boards where the resistance was as low as 20 ohms. But as long as it's greater than 10 ohms, it's probably okay. This step is also very important to do because not all mainboards use the standard PSU pinout. There are many early AT mainboards which use connectors which look the same but have proprietary pinout. If you connect a standard PSU to such a mainboard, it will probably die instantly, so be careful, and when checking the power for shorts, pay attention that what you measure makes sense. 4 ground pins in the middle must be connected together, and of course they are the ground. 3 outer pins on one side have to be all connected together and to plus 5 volts. If you measure something like this, you most likely have a mainboard with a standard AT power connector. So our board here has a standard AT power connector and no shorts between voltage lines and the ground. But what if you would find a short? Well, I can't predict every possible culprit, but in such a case, most common issue is one of the tantalum capacitors. These yellow decoupling caps, which are sitting near the power connector, between the ISO slots or near ICs, these caps are usually used for the voltage stabilization, and if you find one of those shorted, it is enough for testing to just remove it. If the short has gone afterwards, just replace it with a capacitor of the same value. It is, by the way, absolutely okay if you replace tantalum caps with electrolytic ones. Okay, so as I said, we have no shorts. Let's connect it to the PSU and move on to the next step. Check the CPU voltage. For this step, you need to search for the CPU pinout. In this case, we have a 386DX and we want to check if the VCC voltage is plus 5 volts as required. And we seem to have steady 5 volts. Nice. And the next step, check the clocks. Every mainboard has multiple crystals which generate various clocks on the mainboard. For this step, you will need an oscilloscope. First of all, let's check the CPU clock. On a 386DX, this is the pin F12 and the CPU expects double clock there. Let's see. And we are getting 50 MHz here, so the inserted CPU would run at 25 MHz. That looks good. This clock is generated by this crystal oscillator and 50 MHz is what is written on top of it. However, there are more crystals on this board and they all should deliver what is written on the enclosure. This one gives us 14.3 MHz and this is right. This one 16 MHz, also what it promised. This small real-time clock crystal, it should give around 32 kHz. 56 kHz is wrong. Also, the waveform looks strange. It should be a sine wave actually. This looks wrong now, but this crystal controls only the time, and as long as we get something here, it should actually work. Also, 56 kHz is not far away from 32 kHz, so let's pretend for now that this one is okay. Maybe we will come back later to it. But what to do in general if you measure wrong clock or no clock at all? Well, in such a case, I would check the small ceramic caps around and try to replace the crystal oscillators. So, where the voltage and the CPU clock look good, we can go to the next step, inserting the CPU. There is not much to tell about this. You should always apply some dioxide to the socket to exclude any contact issues. As for the CPU, this board expects a 25 MHz 386DX, but I don't have any. However, I have one which is specified for 40 MHz, and it will of course run at 25 MHz just fine. And we can move on to the next step. Power on self-test. For this step, you would need a post analyzer card. When trying to start, the mainboard sends some status information to the ISA bus, which can be read with such a post analyzer. I can insert the card vertically into the slot, but I use additional angled slot razor so you can better see the display from top. Oh, and you should also insert a PC speaker, since some boards don't show any post codes at all, but have only bip codes instead. Most boards have both, however. Right, the reset LED turned off. This means that the reset line is not holding the system back. But there are no beeps and no postcodes on the card, so this board is definitely dead. And we can move on to the next step. Analyze address and data lines. In this step, you can use the oscilloscope to measure the related lines directly in the ISO slot. However, I don't like it to do that way. First of all, the data pin 0 is located just opposite from plus 12 volt on the other side, and if you slip from the pin, you can send 12 volt directly into the data bus, which will kill your mainboard instantly and most probably also burn the chipset. That's why I prefer to use my prototyping board for such measurements. I also don't need to search for the ISO slot pinout since all the measure pins are already marked and visible. It is much more comfortable to use this card. If you find it useful too for repairs or development, you can find the Gerber files in my GitHub repository. Okay, let's see what we have. First, let's see once again that the oscillator works properly. Yep, it does, and we have our 14.3 MHz. Now the address lines. Okay, they seem to be dead. In the background, I'm turning the system on and off to see if there is any activity happening on the address bus, but it seems to be completely dead. Once again, let's see on the reset line. When the system turns on, the reset should go high briefly and then low again. Yes, this looks good as well. Now let's take a look at the data lines. They are all dead as well, hanging high all the time. Yeah, the address lines are also still dead. Some seem to be high, some are low, but I don't see any activity. What does this mean? Well, the address and data bus is often connected through additional transceivers to the CPU and the chipset. Those are usually 74 LS245 or similar ICs. If you measure something strange on those buses, it's worth it to search for those ICs near the ISO slot and check if what is going in and out there makes sense. This would be something what I would do on many boards, but on this one there are no additional transceivers and the buses are connected directly with the chipset. So either the chipset is faulty, what I don't hope, because that would be dead end, or there is something else wrong what controls the chipset. And we are moving on to the next step. Check the BIOS ROM. In this state, this step doesn't make a lot of sense, since we don't see any activity on the buses whatsoever, but this is what I would do at some point anyway, so let's see if the BIOS ROM is alright. First of all, it's worth it to take a look at the sticker, if there is any. The problem is that I got many mainboards which somebody else was already trying to revive, and sometimes BIOS ROMs from other mainboards were installed as I got them. Obviously, this one seemed to be the original one, since we clearly see 36L written on it, just like the name on the board. That is good, and if it works, I can contribute the BIOS ROM image to the Retro Web project. And it looks good. I could read this EEPROM on my computer, and the data seems to make sense. There we see 36L version 1.0, and this looks right to me. So this BIOS EEPROM can go back into the board. Of course with some dioxide again. But what to do if the BIOS ROM is wrong? In such case, you can try to find a BIOS image on the Retro Web project. If you are lucky, someone already uploaded a copy. And if not, try to find a similar board with the same chipset for which the BIOS image is available. If the EEPROM IC is dead, you will have to find a replacement. EEPROMs can be taken from scrap or replaced by a pin-compatible EEPROMs. The EEPROM with a window on top have to be erased with a UV lamp like this one. EEPROMs are easier to handle since they are electrically erasable and they don't need additional equipment. As you see, I always keep a stack of spare ROMs for that purpose. Many mainboards which I get from scrap have those ICs removed, and so I need them quite often. But on this mainboard the ROM is okay, and we can move on to the next step: searching for damages. This step can be made in the beginning, of course, but if you know what works and what not, you can look more closely at places which make sense. And so, since we have seen problems with the data and address lines which go into the chipset, I concentrated more on this area, and I found 3 issues. First of all, near the chipset there is one damaged capacitor. It seems to be on the 5-volt rail and is probably for power stabilization for the chipset. It's not shorted and is most probably not responsible for the problems. It is kind of optional and could only make the system unstable but not totally dead, so we can move on. Down here we have another destroyed tantalum capacitor. It was obviously destroyed by some violent force. The case ceramic enclosure got cracked and this one has to be replaced. However, also this one is not shorted and is once again probably a decoupling capacitor for power stabilization. Once again, something what is probably not causing the issues, which we saw. However, nearby there is some damage to the PCB which was obviously applied by the same action which cracked the capacitor nearby. And this is very interesting. Let's take a look under the microscope. So, here once again the poor tantalum capacitor. This here is the CPU and the traces are going from it up to the damaged spot on the PCB. Here we have a scratch going over the 2 traces, but it looks to be only on the surface. The copper seems to be not damaged. And up here we have a big dent in the PCB. A whole piece of PCB split away and took a part of one trace with it. These traces are going from the CPU to the chipset, and the probability that this is our culprit is very high. So let's fix the traces. it's done, let's check the continuity. Looks good. As you probably noticed, I also removed already the cracked tantalum capacitor. Now it's time for another test. Let's insert the post analyzer card and the speaker once again. Yay! Would you look at that? We have a survivor! The PC speaker beeps periodically and probably asks for some memory. Here I have some memory modules. I'll take 4 times 1 megabyte. 386DX is a 32-bit CPU with 32-bit memory bandwidth. Each memory module is 8-bit, so on this system we have to install the memory in groups of 4 modules. I populate the first 4 slots. These are 8 beeps in a row, which means missing graphics card. Let me add a VGA card and an IDE controller with compact flash adapter as hard disk replacement. Beautiful! We have the post screen. Here is the 386L version 1.0 message from 1991, which we saw already in the BIOS ROM previously. And we have 4 megabytes RAM, which is also right. The battery is not connected, so the message about CMOS settings is okay. Without the battery, it's not able to save any settings anyway. So let's take a look on the BIOS settings. First of all, I have no floppy connected. Drive C, the compact flash card geometry is 987 cylinders, 16 heads and 63 sectors. Makes 486 megabytes. Let's take a brief look at advanced settings. Here we have some memory shadow settings, nothing exciting. And here are memory timing settings. I guess I'll leave everything at default. This video is not about tweaking anyway, we just want to see one happy working mainboard. So let's see if it boots into DOS. Ladies and gentlemen, congratulations! This revived board has booted the disk operation system. Let's see some benchmark results. For example, landmark. Well, 25 MHz 386DX is correct, I would say. One interesting thing is, I don't see any cache ICs on the board. I'm curious if the chipset has any integrated cache. Let's give cache check a go and see what it reports. Well, as expected, this machine doesn't seem to have any cache. That's unfortunate, but at least we should make an ultimate test and start a game. This seems to work as well. Very, very nice. Well, I would almost call it a day. This mainboard is alive again and you hopefully did find this walkthrough kind of useful. After such a fix, I usually cover the repair traces with some nail varnish for protection, and I will have to replace the capacitors later. One thing I would like to show you though. As we tested the address and the data buses, maybe you remember that those were completely dead. There was no movement whatsoever. Now, where the system works, I would like to show you what would it look like if they would work. As you see, the signals are now jumping happily between 5 and 0 volts. Also on the data bus, there is obviously some activity. This is how it should look like on all of the pins. And if you see a signal hanging high or low all the time on one of the pins, this should give you a hint where to search next. As I said, often the bus transceivers are the culprit, but Some boards like this one don't have any, so it depends where to look for. Oh, and one more thing I totally forgot. The RTC clock. If you remember, I measured over 50 kHz on this crystal, which controls the real-time counter. I don't know if you noticed, but the last time we've been in the BIOS, the seconds were ticking about twice as fast. If you look carefully, you can also see how some seconds are even swallowed completely. This is a result of the too high clock which the crystal generates. Let's measure it once again. This time I just use my multimeter. It can measure frequencies up to 5 MHz or so. Well, now it shows 66 kHz. Not exactly what we had last time, but maybe the crystal got even worse and the clock is sliding further away from the spec. Let's just replace it. Here I have a similar crystal, which I took from scrap. It should give us proper 32 kHz. And yay, we have now the expected 32 kHz. Let's take a look at the BIOS time. Well, unfortunately, this BIOS type has an issue which ends up in irregular screen updates, so it looks like the seconds would jump all the time. But let me start a timer and see if it counts properly in average. And yes, this looks good to me. It's just jumpy, but in 10 seconds it counted 10 seconds as well. And this is it. Once again, I hope you enjoyed this how-to and the repair. It is of course just a way how to start, and sometimes you have more complicated cases where you have to study a lot of datasheets, make a lot of measurements, do logical assumptions. But all of that is highly specific for each issue, and it is hard to predict everything what could be wrong for every possible mainboard. However, I hope you will find it helpful, and this how-to will at least give you a good start. Please don't forget to give me some thumbs up if you liked it, or down if not. Every feedback is appreciated. And so far, thank you for watching and goodbye.